Now let's focus on a very special type of one-dimensional motion, so-called free fall. By definition, a free fall is when an object falls or moves under the influence of gravity and gravity only. In other words, we remove other things like the force of the wind, the force of friction from the air, things like that. Then we say it's a free fall. We usually refer to free fall when an object moves only either up or down under the influence of gravity. So it's a one-dimensional motion. When you throw something sideways, it will both move horizontally and vertically, and that is typically called a projectile motion. It's a two-dimensional motion, which we'll be studying in chapter 4. So let's now focus only on a vertical motion as a free fall. So you can see this guy skydiving. He's above the cloud, so there's less air friction unless he moves very fast. So his motion is approximately a free fall, but not quite, because there is actually some air friction, and which will become very important when he opens up his parachutes, if he doesn't want to die, right? Now, imagine if there's no air friction whatsoever, there's only the force of gravity acting on a free-falling object. Then what happens? Do objects fall at different rates? In other words, do they have different acceleration as they fall? This is a problem that has been studied for eons. And if you look at what's happening around you from your own experience, you know, it seems that different objects do fall at different rates. If you, for example, look at a piece of feather and a hammer, they clearly do not fall to the ground at the same rate, right? The hammer falls much faster, and the feather dances around, and it takes a long time to reach the ground. But of course, you realize that is because even though the hammer moves almost like a free fall, there's very little air friction compared with its weight. You cannot quite say the same thing for the feather, because the air friction can play a significant role in comparison to its own weight. So what happens if you remove the air friction? Do they fall at the same rate, or do they fall at a different rate? Or more specifically, do heavier objects fall faster? That seems to be our conclusion from our daily observation. Typically, heavier things do fall faster, like the hammer versus the feather. And that seems to be a fixed notion for a lot of people. But is that really true? Well, it took a genius to not only question the validity of this claim, but also to show that it doesn't work. It's not like that. And that genius has a great name. I'm sure you have heard about this before. His name was Galileo Galilei, a great Italian physicist. What did Galileo do? Well, he achieved many things. For example, he made a telescope. He was able to look at the moon through this telescope and found an area which looks like an ocean, so he called a sea. Okay, actually was not a sea, but at least he was able to see some details. And one of the things that he did was that he went onto the Leaning Tower of Pisa. Right? There's a picture of Leaning Tower of Pisa. And what did he do when he reached the top of the tower? He did an experiment. He had a heavy ball and a light ball, and he dropped both of them simultaneously from the top of the tower. And he wanted to convince the audience, the spectators, that even though they have very different weights, they would reach the bottom at the same time. And there is a cartoon picture for that. So he says, apply for grant, and all they did give me was a big ball and a small ball. So that's what I'm going to do. Well, if you know the story, you know what happens, right? Even though they have very different weights, they hit the ground at almost the same time. Now I say almost the same time, but if you really pay close attention, you might find actually the heavier one did fall a little bit faster than the lighter one. So it's not 100% proof that they would fall at the same rate, because even though they have very different weights, they almost hit the ground at the same time. It's not precise. And of course, you might argue that is because of air friction, a different amount of air friction on these two objects. So the only way to show them experimentally, to convince everybody experimentally that everything will fall at the same rate in a true free fall, is to create a free fall environment. And that is to remove all air friction, right? And that is the definition of a free fall. Otherwise, it's not really a free fall. So Question is, how does one remove air friction? Well, you can do it in a vacuum tube, but there was no vacuum tube back then. Or if Galileo had his way, he would go to the moon, because he may not know it, but it turns out that there is no air on the moon, okay? And therefore, there is no air resistance to speak of. So you could do this experiment on the moon. You could take these two balls, or more dramatically, you can take a feather and a hammer and drop them on a lunar surface to see whether they hit the ground simultaneously. But of course, you couldn't do that back then. So did Galileo just give up? No, that wouldn't be Galileo. He was such a brilliant physicist. So he said, all right, I cannot quite create a true free fall by removing all air friction in the real world. So I'm going to do it in my head. Okay, so instead of performing this experiment in the real world, he performed it in his head. And that is called a thought experiment. So what happens if we do the experiment on the moon? Well, we're going to talk about it a little bit later. You cannot do that in Galileo's time, at least. So he would do what's called a thought experiment or ideal experiment. So why do we call it ideal experiment? Because you remove any air friction. So that's an ideal free fall. And he could only do it in his head. So how did he convince everybody else that whatever he did in his head actually was correct? Well, here is what he did. Here is his argument. He used logic to convince everybody. So here's what he did. He says, let there be two balls, a big one and a small one, okay? A big one and a small one. And let us assume that the big, otherwise known as heavy one, will fall faster than the light and small one. He says, I want to show you that this is just impossible. Why is it impossible? Because that would lead to a logical absurdity. Okay, logical absurdity. So how does that work? Well, he says, look, you want to claim that the heavier one falls faster, right? Because the heavier it is, the faster it falls. But most people believe that, at least back then. So let me draw a vector indicating its acceleration, and another vector indicating the acceleration of the small one. It's shorter vector, therefore indicating that the heavier one falls faster with greater acceleration. Now, what happens, he says, if I tie these two objects together? Okay, so I am going to do this. I'm going to duplicate it. Okay, I'm going to tie them together. So I'm going to move this guy. I'm going to tie them together like this. Okay. Now, of course, now you end up with an even heavier object, right? I'm sorry. What did I do? Let me duplicate this again. Let me duplicate this guy and put it over here. And let me duplicate this one, also put it over here. I'm going to put them together like this. See what I mean? Okay, I'm going to tie them together. So you end up with an object that's even heavier than the red sphere, because it's red plus the blue one, right? It's even heavier. And according to the logic of most people back then, because this is an object that's even heavier than the red sphere, it's going to have an even greater acceleration, right? Even greater acceleration, because the heavier the object is, the faster it falls. However, he says, you really think about it. What did you do to the heavy ball? You tied a lighter one on it, right? So as the heavy ball tries to go downwards, the lighter one, being lighter, falls behind. And so when you tie it to the heavy one, what do you think the lighter one is going to do to the heavy one? It's going to drag the heavy one, right? So it's going to prevent the heavy one from going down as fast, right? So therefore, on the one hand, when you tie them together, you get an object that's even heavier than a heavy ball, so it's going to fall faster than a heavier one. But on the other hand, wait a second, it should be slower than a heavy one, because you tied to a lighter one to it, and therefore the lighter one is going to drag the heavier one, therefore you end up going slower than before. You can't have two contradicting conclusions for the same experiment. It just doesn't happen. It's either one way or the other. You cannot have it both ways. So what does that tell you? The assumption that the heavier the object, the faster it falls. turns out to be what? The condition that leads to this logical trap, logical absurdity. So the only thing we can say, the only conclusion we can draw here is that the original assumption was wrong. What's the original assumption? The heavier the object, the faster it falls. By the same token, we can show that you cannot say the lighter the object, the faster it falls, because you can fall through the exact same trap. So what is the only way out? Well, the only way out is that they fall at the same rate. It doesn't matter whether you tie them up or not. Nobody's dragging anybody else. It's always fall at the same rate. See, this is his idea, his thought experiment. So he simply said, let there be no air friction in his head. Okay, he used this brilliant logic to convince everybody that everything should fall at the same rate in the absence of air friction. This argument, if I can see your face, okay, as I've seen many times, my students, when I explain this to them, it would often bring a smile to their face. Hundreds of years later, the powerful, brilliant logic of the great Galileo Galilei still lives. This is really incredibly simple, elegant, yet powerful. Okay, so we should be convinced that everything falls at the same rate in a true free fall in the absence of air friction. But going back to doing this experiment on the moon, now people went to the moon, so we can actually do this experiment on the moon. And guess what? Somebody did. Okay, let me share a new screen with you. I can show you the actual YouTube video, which is a recording of what an astronaut did on the moon.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Wow, look at that. Okay, let me start the video. So I hope, the video was kind of grainy because, after it was done in the 70s, it was on the moon too, but I hope you saw that the hammer and the feather did hit the ground, the lunar surface, at the same time. So Galileo was correct. Amazing. I wish he could see that video, but I'm sure he was already convinced that he was right. All right, so going back to our presentation. All right, so everything falls the same rate at the same place. Otherwise, you would fall into logical trap. So that means A equals G. G is the acceleration gravity for every object in a free fall. Now, G does vary and can vary. It does vary from place to place, but in the same location, it must be the same value. Okay, here on the surface of the Earth, if you look at, if you round to only the first two sig figures, G equals 9.8 meters per second squared. And it does vary from region to region. It is the smallest on the equator with a value of 9.77 meters per second squared. And it's the greatest at the two poles to 9.83 meters per second squared. So not that different. Therefore, and if you only look at the first two sig figures, it's 9.8 meters per second squared, and that's what we usually use. Okay, if you don't specify the region. Now, if you know exactly where you are, then you can have a better reading of the G value locally. Here in Pasadena, it is equal to 9.7946 meters per second squared, and we have an experiment, free fall, that measures the acceleration gravity in our lab room in Pasadena. Our equipment is not accurate enough to give us 5 sig figures, but we can get the first 3 sig figures, hopefully 9.79 meters per second squared. Okay, now what does this G value mean? It means that the acceleration is such that with every passing second, the velocity will change by 9.8 meters per second downwards. Okay, so if an object is going downwards, if it's going downwards already in a free fall, then at every passing second, it will increase its speed by 9.8 meters per second. And when it's going upwards in a free fall, then of course it will slow down. So on its way up, the speed will decrease by 9.8 meters per second with every passing second. Okay, so if you start with 0 speed going downwards, then after at the mark of 1 second, so 1 second into the free fall, how fast is it moving? 9.8 meters per second. At the 2 second mark, how fast is it moving? It's you add another 9.8 meters per second. So therefore you get 19.6 meters per second, and so on. Okay. So how does G, this acceleration of gravity, compare with the acceleration of a fancy sports car? Now you might wonder about this. You drive a car, obviously, and one of the things that's desirable is a great acceleration, right? And that's typically measured in the number of seconds it takes to go from 0 to 60 miles per hour. We can convert that to meters per second. Okay, let's suppose, or vice versa. Suppose I have the acceleration of G. Suppose the car can accelerate at a rate of 1 G, or 9.8 meters per second squared. At this rate, how many seconds would it take for it to reach 60 miles per hour? Well, isn't that interesting to know? Let's do that. Let's do the calculation. Okay, so if A equals G, the time t it takes to reach from 0 to 60 miles per hour will be what? Well, let's see here. V equals AT, A equals G in this case. Okay, so V is 60 miles per hour. We need to convert that to meters per second. You notice that every mile is 1609 meters, and every hour is 3600 seconds. And so that's how we convert it to meters per second from miles per hour, and you divide it by G, which is 9.8 meters per second squared. If you do the algebra, you get 2.7 seconds. Wow, it will take only 2.7 seconds for this object to reach from 0 to 60 miles per hour if it has an acceleration of 1 G. That's quite a lot. You can compare with the car you drive and see whether your car can do that. Unfortunately, most cars cannot do that. Okay, most cars fall quite short of that. But we can take a look at some fancy sports car. For example, I have given you 3 examples. I'm sure you have other examples to think about. Here is the 2021 BMW M3. It's a fancy sports car by all means, and you can check the data. How long does it take for this car to reach from 0 to 60 miles per hour? You can check the data. You'll find the answer is 4.5 seconds. Okay, so no, it's not 2.7. It's not even close. So you can express the acceleration in terms of G. So it's let's see here, 2.7 divided by 4.5, you get 0.6. So you know it's 0.6 G. Okay, because the acceleration is such that you know, if the acceleration is 1 G, it will take only 60% of the time to reach there, and therefore this for this guy, I can write A equals to 0.6 G. Okay, next I have the Porsche 911 Turbo 2021. This car is even more expensive and it's even faster. And if you checked the specs, you'll find that this car can reach from 0 to 60 miles per hour in 2.9 seconds. A great improvement over the BMW, but still, it is not quite at 1 G yet. And how many Gs would that be? Well, you take 2.7 divided by 2.9, and you're getting 0.93 G. Okay. Wow, we're almost there. Are there cars that are capable of going beyond 1 G in acceleration? Well, for many decades, that was not possible. But things are progressing. Today, there are examples, even though there are very few examples of cars, production cars, that can exceed 1 G. You will see in chapter 6 and 5 and 6 why is it so difficult to break 1 G for a car. But there is an example that I want to give you, and that is the Tesla Roadster. The Tesla Roadster, if you do a search, how many seconds does it take to reach from 0 to 60 miles per hour for this Tesla Roadster? It's all electric, by the way. And the answer is 1.9 seconds. Wow, look at that, 1.9 seconds. Okay, so, you know, you take 2.7 divided by 1.9 this time, you are getting what? 1.4 G, wow. So A equals 1.4 G. You are getting greater than 1 G of acceleration. So if you step on the acceleration pedal in that car at full throttle, you will find the car will jump forward and you will feel a push from the seat, which exceeds the sensation of your weight. You'll be really pushed hard by the seat, and you'll be accelerating 40% faster than 1G in a free fall. Okay, so yeah, the Tesla Roadster. Anyhow, now let's continue. We're looking at some simple numbers here for how the speed changes as a function of time in free fall. So I have here this example. This person drops an object in a free fall. So at t equal to 0, the distance traveled is 1 meter. And at t equal to 1 second, the distance traveled is 4.9 meters. In 2 seconds, it's 19.6 meters, and so on. How does that work? How are these numbers obtained? Well, it's a uniformly accelerated motion, right? We spent a lot of time convincing you that's a uniformly accelerated motion, the acceleration being g. So therefore, I can write both the velocity and the displacement as a function of time in a free fall. So if I choose a downward axis like this, okay, we call it x, and starting from here, they use d, we call it x, doesn't matter. So v would be equal to v initial plus gt. G is the acceleration v or v naught plus gt. But of course, you can also set v naught equal to 0, like as what they did there. And x would be equal to what? X naught plus v naught t plus 1/2 at squared, or gt squared in this case. Right? I've chosen downward as positive, by the way. So if you set v naught equal to 0, so the ball leaves his hand at 0 speed, and we set also x naught equal to 0, so the ball leaves at the origin of the coordinate system. So you set v naught equal to 0 and x naught equal to 0. Then you end up with v equals gt and x equals to what? 1/2 gt squared. Right? So g is 9.8 meters per second squared. So after 1 second, you can find v, which is 9.8 meters per second squared. After 2 seconds, it's 19.6 meters per second squared, and so on. 19.6 meters per second, that is. And as far as x is concerned, if you plug in t equal to 1 second, that's 1/2 of g times 1 squared, so it's 4.9 meters. That's what you see right here. After 2 seconds, you plug in t equal to 2 seconds, so 2 squared is 4, 4 over 2, that's 2. So it's 2 times 9.8, that's 19.6 meters, and so on. So that's how it goes. Okay, if we were to plot velocity, acceleration, and position all as a function of time, if I choose the upward direction as positive this time, okay, upward direction, not downward direction, so upward is positive, then if the ball leaves your hand at 0 speed, then the ensuing velocity of the ball would all be negative because it's going downwards. So you see here, it's downward. Okay, so velocity is negative, right? It's negative. It's below the 0 axis. It's downwards with a slope of negative 9.8 meters per second squared. Why negative? Because again, I chose upward direction as positive in this context. So g, so the acceleration is negative 9.8 meters per second squared. And the acceleration is, again, below 0. The 0 is right here. So there is a negative sign, okay? There should be a negative sign here. Negative sign, right? 0. And position, you start from the certain height. So this time the height, you choose the height somewhere here, the 0 of the height somewhere here. So he starts from a certain elevation somewhere here, and then he drops the ball like this. So initially x is a positive number, then it goes down, okay? It goes down. So the way you would write it here is you would have a positive x naught here, okay? You would have a positive x naught here, and v naught is equal to 0. And g should be replaced with negative g because we're choosing downward as negative and upward as positive. So a is negative g in this case. So you have a parabola curving downwards, and that's what you see there. That's what you see there. Okay, so that is, you know, some very basic application of the uniform acceleration formulas that we obtained in a previous lecture to this very famous special case of uniformly accelerated motion, which is the free fall. In our next lecture, we're going to look at some more complicated examples of one-dimensional motion with uniform acceleration.